All righty, so I think we'll get started here. Thank you everyone for joining today's iteration of the Data-Driven Science and Engineering seminar series. Today we have the pleasure of hearing from Professor Themis Sapsis at MIT. Professor Sapsis' work lies on the interface of nonlinear dynamical systems, probabilistic modeling, and data-driven methods. And today we're going to be hearing about optimal sampling and extreme event-aware learning. So thank you very much to everyone for being here, and thank you, Professor Sapsis, for your seminar.
Thank you very much for the invitation. It's a true pleasure to give this talk, and I look forward, hopefully it's going to be interactive. I would look forward to hear comments, questions, and so on. This is a summary or an overview, a quick overview of the past work we have been doing in my research group, meaning, the last 6-7 years, but also the second half is new work that is hopefully going to be published soon. What I call extreme event aware learning. And let me start with some motivation. As the title says, we're interested for systems exhibiting extreme event behavior and to build mathematical theory, applied mathematical tools, so that we can quantify, we can analyze, we can optimize with respect to these, events. So the definition of extreme events, very informally, we are basically talking about large deviations from normality. It is important to make a distinction between what is rare events and what we call extreme events, right? So rare events is essentially any low probability event, right? That doesn't have any other special properties other than just being a very low probability event. For example, winning the lottery. This exact combination of numbers, it doesn't have a special property other than, being rare among the vast possible combination of numbers. An extreme event, on the other hand, it's not just associated with low probability. There is some physics behind it, there is some dynamics behind it, and that's how we will see it in this context is essentially the result of the synergistic action between some low probability events and some non-trivial dynamics, right? So the dynamics can be an instability associated with nonlinear dynamics, some sort of self-organized criticality, a feedback loop. In any case, again, it is the synergy between a low probability event and some non-trivial dynamics, and that's what makes the extreme events different from rare events. Let's see some examples that probably many of you are familiar with. Again, referring to nonlinear dynamical systems, a slow-fast system, right, where you have a slow manifold, mainly attracting solution, except some perhaps islands where you have these jumps, these instabilities, and these can be seen in the context of extreme events. Like, people have analyzed these things. Again, they belong in the general class of low-dimensional systems, in the sense that there is a slow manifold, and in principle you can reduce dynamics there and understand instabilities. Noise-induced instabilities, this is the standard setup for large deviations theory and so on. Essentially, you have some nonlinear dynamics coupled with some weak noise, and then you try to understand especially transition probabilities and so on. And then the homoclinic, heteroclinic cycles, like more global phenomena, right? You have jumps from one equilibrium to the other. Again, things that have been studied very seriously in the context of low-dimensional dynamical systems, which have incredible value. And again, people have done a lot of serious work there. The context we are discussing today, it's slightly different from the things that I just described, in the sense that there is a high-dimensional attractor. Essentially, it's not easy or it's not possible to reduce the system dimensionality, the effective dimensionality, again, because there is a high-dimensional attractor. How high? It can be infinite dimensional. It can be thousands of dimensions, but it certainly cannot be reduced, to 10 or 50 variables. And then you have these islands of instabilities that you see here, where whenever the system undergoes through these islands, there is some sort of jump, there is some sort of extreme event. And this is the picture that we will keep in our mind as we move forward. And we have, again, in the past, we have written papers discussing those and putting them in the context of the broader context of dynamical system. So the setup of the problem, how we will be working on these problems, essentially, we assume there is some sort of input space, and this can be high dimensional, meaning more than, order of 50 dimensions. So there is an input space. This can define parameters, they can be initial conditions, it can be excitation parameters, anything that defines, the input space. We have a very high dimensional state space, and that's why going from the parameter space to the state space, it is a very expensive thing. And except if you have equations that you can solve, which again, it is very expensive, we will typically assume that this is unknown, right? Or it's known, but with very high cost. And then at the end, you have the observable space, like the space of observables, where basically you take the state space, you have a functional, you transform this to some sort of observable, very low dimensional, right? And for which you are either interested, basically you're typically interested to find the statistics of this thing, right? Tails, low probability events, everything that is of interest lives here in the space of observables. So G is known, right? But again, it's not trivial how you go from the input space to the state space. So the first class of problems that we are interested in is to understand what data or what set of parameters from the input space is the most informative or valuable to model extreme events, to understand statistics in the space of observables, right? And the setup we will be essentially adopting here, it follows the active learning paradigm, where you have some acquisition functions, and I mean, we will be developing acquisition functions for extreme events. Optimality is, something we will be defining and studying there, like optimality in the sense of most informative data points. And then we will also discuss some applications, right? So that's the first part of the talk. And as I said, there is a plethora of problems where we find value on examining extreme events. And I'm an ocean engineer, as Nathan mentioned, there is a boat behind me, model. You see here an offshore structure. This is like multi-billion-dollar investments, right? And the waves. You see a container ship, and this is actually a real footage, as you can see. It's 7-8 years old, so it's not AI. We are talking about 25-30 degrees, listing angle, very, very high roll angles, flow separation in helicopters. And again, the question there, like what engineers or ocean engineers or aerospace folks they want to understand is to characterize the full PDFs with a minimum number of numerical or actually physical experiments. The second class of problems is geophysical systems, and the key difference between this type of problems and this type of problems is that in the second case, you don't really have controllable data. In other words, if someone tells me, like this is the set of initial conditions that you should try because this is very informative for your data set, it's not actually even possible to go and try to initiate a climate or weather model with this exact set of conditions. So you basically need to work with the data that you have. And this is life, and we have to live with that. So in this case, the question is how we can quantify the value of its existing data point and use those that carry the most critical information for extremes, right? So in the first case, we can go and probe the solver for the points where we think they're most informative. In the second case, we can only compromise with the fact that we can select a point from a big data set. So the paradigm, like active learning paradigm, I assume you have seen it in one way or the other. You start with some, pairs of data, input-output pairs, and you do some learning, let's say Gaussian cross-regression or any type of probabilistic learning. The important thing is that you need to have an idea of the epistemic uncertainty of your model, meaning where the model thinks it goes, it is wrong. You select the input based on this information, you derive or you write down some acquisition function, which is the criteria that is telling you where you should sample next. And then you develop the new experiment, you set it up either at the towing tank or, at your big computer, and you repeat this cycle. Eventually you have a surrogate model for how the data are connected with each other, meaning input output. And from there, you can either quantify risk or you can do optimization with respect to extremes. So that's the key idea. Acquisition functions, there is a large number of those. The standard literature of machine learning, right? The basic idea is you try to find a new point or a new sample that minimizes the uncertainty of your model, right? The local uncertainty is a decent or a reasonable start. So basically, I select a point where I feel that it's going to reduce the uncertainty of my model wherever the uncertainty is going to be very large. Another idea along these lines is to do some sort of more global description of uncertainty. So you basically weight or integrate or average the uncertainty of your model according to the probability that any of these input parameters will appear, right? So you take this integral and you try to understand what will be the impact of a hypothetical new point x star on this sort of integrated notion of uncertainty. And then there is mutual information ideas, right, where you try again to optimize the mutual information. And there are issues with all of those for various reasons, right? Mutual information, it's super expensive, so it doesn't really fly for high dimensions. Uncertainty, on the other hand, it's a nice idea, but it has a very important pathology for extreme events. And this is that it doesn't take into account the impact or the value of the output. So let's see that very simply, right? For Gaussian process regression, you see sigma n square. I will go back, one slide back, and I will show you this formula. You will see that's the covariance function for Gaussian process regression. And if you notice, the covariance, it depends only on the input values. It doesn't really matter if the output at this location is large or small, which means that uncertainty, the way it is written here, the uncertainty of the model, it does not really take into account if this is a very large value, which contributes to the statistics of extremes, or it's a small value that has no role for the extremes. So if you just follow these two criteria, you basically don't learn necessarily good information for extremes. You try to improve your model in regions that may have nothing to do with extremes. So the statistics of the tails will not converge very effectively. And in fact, you can show that asymptotically, meaning for sufficiently large number of samples, when sigma goes to 0, even the mutual information behaves like that. So it's not like mutual information, it's just a computational problem. It doesn't really tell you much anyways. So motivated by this idea and the discussion I had before that, the extreme events are those that eventually contribute to the tail, we start thinking differently. We start thinking in terms of the output probabilities densities. Basically, this is our model, right? The y of x. For each of those curves that you see here, like you have the mean estimation, and then you have the mean estimation plus one standard deviation, where standard deviation is meant in the sense of uncertainty of the model. So for each of those, there is an associated probability density function for y, right? So I have the PDF of x, I have the map, I can compute the PDF of y. And the idea is, instead of trying to converge at the map level, I'm trying to converge at the level of statistics for the specific observable I'm interested in. That's very different because the second notion of convergence, what I have on the right, is essentially much weaker. But guess what? This is exactly what you are interested for extreme events. You don't really need to know the full map. You need to know the map in the regions that matter to compute the tails. So that's very, fundamental. And that's what we do. We formulate an acquisition function with respect to the output PDFs of the observable of interest. So that was work that we did, back 7 years ago. And the idea again is choosing inputs through the lenses of the output PDF. And this is the criterion we had introduced at that time with a former student. The good news is that it really compared with the uncertainty sampling that I mentioned before. This one, because the probability density function of the output, it is explicitly written in terms of the model information. It takes into account the input-output relationship. Therefore, it knows where the extreme events are, and it tries to allocate resources there. So that's all good news. The bad news is that this is very expensive, right, to compute. So even if I want to optimize, this is super, super expensive because you have PDF for different X stars, which are the candidate points. You have to compute a new PDF with the tails. This is very, very expensive. So we had applied at that time only on two-dimensional inputs, basically 2D parameter spaces. A nice problem. We had an offshore structure that you see here, smooth particle hydrodynamics code, very expensive to run, like it's run, meaning 20 to 30 seconds wave group, that hits the structure. It took like a day or 2 days to compute in GPU. But the good news, again, because we had one-dimensional waves, we could do two-dimensional parameterization of the wave. So we basically had to sample in this X1, X2 space. X1 is the length scale of its wave group. X2 is the amplitude of its wave group. And you can basically show that with just 16 iterations, meaning just 16 input parameters, you get the tail, the probability density function for an observable. That was, I believe, the stress acting at the root of the offshore structure. You can get it right up to 3 sigmas, right? This is just 16 experiments, very, very small compared with like thousands that you would need to do this type of statistics. So as I said, that was nice 2018 work, but it worked only for 2 to 3 dimensions. And if we want to go higher, like realistic C states or any other type of problem, for engineering problems, you need at least order 10 or order 20 dimensions, if not even more. So it's not going to fly for this dimensionality. And this is where we asked our question, whether we can derive an alternative acquisition function that still has these nice properties that I just discussed, but it is appropriate for higher dimensions. And the answer is yes. And it comes through an asymptotic upper bound that basically says that the quantity that we had, defined as a criterion, it can be bounded from above using some Sobolev inequalities. It can be bounded from above through the quantity I have here. I'm showing here on the right. Basically, this quantity is what? It's essentially the posterior uncertainty estimate of my model, right? That's sigma n square, weighted according to the probability density function of the input. Like the numerator of this quantity is the integrated variance that I mentioned before at the beginning. But there is an extra term that is super interesting here, and it's the probability density function of the output, right? Now, why this is a good thing here? Because basically, if you have an output, a value y, an x that is associated with a value, output value y, that is very extreme, it's also going to be rare, which means that this term is going to be very, very small for extreme events, which means that the error of my model is going to be penalized more for extreme events. And the even better news is that this is also weighted according to the probability density function of the input. And in this sense, there is some sort of competition, if you want, between how rare the input is and how rare the output is, because you want extreme events to matter a lot, but you don't want completely exotic extreme events to dominate your problem. This is guaranteed by the P of X term. If you have a completely, like a big extreme event that is completely exotic, meaning it will never happen, P of X will take care of it, right? So it will be essentially multiplied with a very small weight. So that's the mechanics behind this upper bound that I'm showing here. And the great news is that this is very easy to do gradient optimization with. So you don't really have to mess with all the computational obstacles that we had to deal when we were working with the left-hand side. So, and I mentioned already, there is the error, there's the emphasis on inputs with high probability, the P of X, and there is the emphasis on inputs leading to large outputs, which is the denominator. So all nice in this sense. We call this the likelihood weighted acquisition function, and we had applied, numerous problems. I will show some of them. But before I go there, I want to talk a little bit about how well or how close this upper bound is to an ideal acquisition function. But before, we even talk about that, we have to define what is the optimal acquisition function. So let's try to think of the best acquisition function for extreme events, right? If we can talk about such thing. And the way we define that is basically from the criterion I mentioned here. Let's say that P of Y is the exact but unknown probability density function that we're trying to capture. We will call the optimal acquisition function, or criterion, the criterion that basically minimizes the distance between the approximate model, the PDF of the approximate model, and the PDF of the exact but unknown or a priori unknown PDF, right? And you see I'm using the L1 of the logarithms of the PDFs because I want to emphasize the tails. I'm not doing KL divergence because KL divergence has an extra term P of Y here that is getting very, very small for large values of Y for extreme events. So that does not really help me, to quantify extreme events. So that's why I'm using L1 of the logs of the PDFs. So this is, again, in an idealized world where I would know the exact map, this would be the optimal criterion. Now, in the real world, I don't really know this map, right? The only thing I know at any iteration is some points of this map. The space of functions that satisfy specific sets of points, it's essentially can be described very nicely by a kernel Hilbert space. So what I'm doing is essentially define the selection criterion. This is the optimal acquisition process through what I'm showing here. Essentially, it's the minimum, it's the quantity, it's the point X star that minimizes the supremum over the reproducing kernel Hilbert space, meaning all the functions that satisfy the points I have already sampled, the quantity that I have in here, right? So again, in a very nice theoretical world, this would be the best point, or the best acquisition function in terms of selecting points. Now, going back to reality, this is a very, very hard problem, optimization problem to solve. It's an intractable minimax problem, right? It's supremum over an infinite dimensional space and minimum over a high dimensional space. So we have to somehow, compromise with something else. And this something else comes in the form of an asymptotic expression for exactly the criterion I just showed, that this asymptotic expression says that if your sigma is relatively small, then you can basically expand, you can do an asymptotic expansion of the criterion and write it down as I'm presenting on the right-hand side, right? So what do you see on the right-hand side? You see again sigma, that's the error, and you see an interesting weight that involves the probability density function of the input and involves also in the denominator the probability density function of the output. Okay. Now it turns out that you can actually use a Cauchy-Schwarz inequality, and from there you can rediscover the criterion that we had derived as an upper bound before, right? So in short, either this criterion that is coming as an asymptotic limit of the optimal criterion or the Cauchy-Schwarz upper bound, these are both very close to the optimal. I mean, the left is exactly the optimal in an asymptotic sense. The right is just a Cauchy-Schwarz step away. So that's what we will be using. And again, now we have confidence that this is actually really, really good in terms of optimality. And we go to, I mean, more realistic problem. This is a Navy vessel that people are interested to quantify the midship section, the stress at the midship section. It is operating in random seas. And in fact, this is DDG 1000 for those of you who may be, familiar with national security things. So we represent the stochastic C, as you can see here. We keep quite a few terms. I believe this is like 10 terms that we're keeping for the stochastic C's. We represent the vertical bending moment at the midship section, again through a Cahuren-Loew expansion. And the key idea is to map the coefficients that describe a finite time wave group to the coefficients that describe the vertical bending moment. So basically, we need to find this map, Qi of alpha, and that will immediately give us the statistics of the vertical bending moment, right? And here are some results. And what you see, the bold black line, it's 10,000 hours of simulation. So 10,000 hours of physical time. You just simulate. This takes like weeks to do that. Every different line you see is simulations obtained with an 8, 16, 24, 32, or 44 wave groups. And every wave group is associated with 2 minutes, right? So 16 is basically 32 minutes versus 10,000 hours. And you see how well it works, right? With 44, it's basically an hour and a half. The yellow, it's almost spot on the 10,000 hours. So that's very, very efficient. And we have, some regulations have been rewritten to work with this approach and so on. We also applied it in a different system. That's the MMT model, Maida, McLaughlin, Tabak model. It's a one-dimensional dispersive wave turbulence model. Essentially, it's a nonlinear Schrödinger equation. As you can see here, you can recognize the nonlinear Schrödinger term, the cubic nonlinearity. But instead of having a Laplacian, you have a pseudo-differential operator where alpha is 1/2. So the pseudo-differential operator is associated with deep water waves dispersion relationship, right? And you also have a selective Laplacian here, so it dissipates the very high frequencies. So that's the system. And I mean, if you run it forward, you can see that there are extreme events forming. So horizontal is X, vertical is time, and you see these extreme events forming spontaneously in various locations. If you do the statistics, you will see that this is how it looks like, right? Very heavy tails. And we aim to see if we can compute the statistics, these very heavy tails that you show, for a finite time horizon. So the idea is that I represent the initial conditions. I have stochastic initial conditions, 20 dimensions. I just expand my Gaussian initial conditions, in space with the PCA expansion. I keep 20 dimensions. Here we use an ensemble depot net to represent, as a regression model, if you want, for the supervised learning piece. We didn't use Gaussian Pro's regression because it's 20 dimensions, it's too high for GP. And the way we estimated the uncertainty is through a simple ensemble set of neural networks. Basically, we trained for the same data set, the neural network, multiple times, and then we got the uncertainty from that ensemble. So long story short, again, the idea is to try to see what are the statistics of the spatial maximum of the solution after a finite time horizon t. And I want to show you the comparison before I show any statistics. I want to show you the comparison between a Latin hypercube sampling strategy and the likelihood weighted sampling strategy. So in the Latin hypercube sampling, which is very popular for this sort of sampling problems, what I'm showing is the initial conditions that were selected, right? So this cloud of curves, they indicate the initial conditions that were selected for sampling these statistics. And they are colored according to the maximum value after time t. So basically, the darker the initial curve is, the initial condition is, the larger its value at the time of interest. And what you see here, very interestingly, is that the dark trajectories are basically the ones that are already big from the initial condition states. So what Latin hypercube sampling does, it's basically selecting trajectories that are already very large initially, and they may become a bit larger, but it is not able to discover the unsuspecting initial conditions that eventually become large, right? Which is what the likelihood weighted sampling does. You see that all trajectories are more or less very small initially, but many of them have very dark values, right? Because they become very large down the way. So that's the big difference. Likelihood weighted sampling is able to discover the unsuspecting initial waves. And if you go and see how things converge with respect to the metric we had defined at the beginning, which is the log of the probability density function through the approximate map minus the log of the exact PDF, you basically see that with the likelihood weighted approach, which is the red and the blue, you have very good results, right? So this is W, as you can see, the likelihood weighted. If you do uncertainty sampling, by the way, you get into this very popular double descent issue. The more you sample, the more you diverge until you converge much later. With likelihood weighted, you have nice monotonic convergence. And then we applied all this to the problem. This is the two previous problems were associated with what I would say engineering problems, where you are able to select the initial or the parameters and then you can run the model. This is a different problem where you are basically working with a fixed data set. This is a climatology data set, and we are interested to find the most informative data for quantifying the extreme heat waves over Paris, for example, right? And again, this is different from the previous problem because now we have a fixed data set. We are not allowed to go back and ask the climate model, can you run this particular initial condition? No, we have a very big data set, and we're trying to see which points in this data set are the most informative for extreme events. And it turns out that the way we are actually approaching the problem is that we are clustering the points, the full data set, into 6 clusters. And this is the frequency of these clusters, right? Again, we are using the ERA5 data set to identify the frequency and the clusters. So this is the frequency. And then when we apply the likelihood weighted machinery to quantify statistics of the temperature, we see basically that the optimal data is very different from the most frequent data, right? So it turns out that the most of the optimal data live in the least visited or frequent cluster, which is number 6. And if you notice below, the cluster number 6 is associated with this sort of blocking pattern, they call it in climatology heat dome, that you see here. And this is where actually these are the events that are the most informative in order to get the correct statistics. So on the movie, you see how things converge with respect to the number of iterations In every iteration, we select an additional, I believe, 50 or 100 data points from the big data set. And you see nicely that with the US likelihood, I mean, the uncertainty sampling likelihood weighted, you have convergence with 145, data points, essentially, right? While, with Monte Carlo, which is just randomly picking points from the big cloud or the initial set, you have a large number, but I mean, it doesn't really help. It will help much later. Okay, so with that, I want to close. This is work again that we've been doing. Actually, the last slide was just published a week ago, but we start thinking a year and a half ago differently, right? We start thinking in a different way, and that came actually from practitioners who were basically asking us, okay, if you have some extreme events, then yes, you can guide your acquisition function so you can nail them down. You can find all the statistics around this extreme event, but you start with the assumption that you have at least even some very few extreme events. What if you have no extreme events in your data set? So that comes now the second part, which is what we call extreme event aware modeling. And the question here is, how can we learn models aware of extreme events without relying on extreme event data, right? And I will go back to the setup as we discussed it. And again, this is the same exact setup. You have an input space. And there is a difference because now in the data set that I already have, I don't assume that I have parameters that gives me a state that is giving me extreme events. That's very, very different because now I have no idea where and if there are any extreme events. What I assume instead in this version of the problem is that I have some data for X and U, right? Not extreme. And I have some statistics for the observable, which I didn't have before. So now I have statistics for certain observable, some observable, including its tail. And that's the only thing I have available, right? Together with some data set that is not associated with extreme events. And the question is, can I learn a map that takes me from the input space to the state space that is consistent with the observable that I have in hand? And it's telling me that, oh, there is a tail, heavy tail there. So something is going on, but I have no data set that or data points that indicate that. So basically, you are forcing now the learning problem to give you maps that can explain some extreme events you have at the observable level. So the way we formulate the problem is that we are given some data. As I said, X, the input data point, U, the state, and the value of the observable, Y. And I don't assume that D contains any data for extreme events. So all these are associated with normal values of Y, nothing extreme. But I'm trying to find now the U, the approximation of the map from X to U, that is consistent with the probability measure for an observable Y, right? So I assume that I have the statistics of Y, and I want to find the map U hat that is giving me a probability density function that is consistent with the probability density function of the observable. So as I said, we are trying to encode in the learning process the consistency with the probability measure of an observable. You could also, like we can discuss about that, like how that will be formulated. And again, we are essentially pushing the learning towards maps that explain the observable statistics. Now, the question is, where are you going to find this measure, right? Where are you going to find the exact statistics for your PDF of a given observable? And for many applications, it turns out that this is available It can come either through a reduced order modeling argument, through prototype models. And I mean, unlabeled data is the most common one, right? And we will discuss an example. There are situations where you have unlabeled data, and from there, actually a huge number of unlabeled data, from there you can compute statistics for an observable, but you don't have labeled data, so you can learn the map. So this is a very, very good setup for this type of problems. All right, let's try now to get into the mechanics of how this is possible, how this is done. And by the way, we call this ETA learning. ETA comes from extreme event aware, EEA or E2A or ETA. So we have, we're trying to see where the mean square, error fails. So let's say that Y of Xi defines a map in the standard mean square error sense. So we will show that when extreme events dominate the error, and this is reasonable if we have no data for extreme events, then if you do things with mean square error, this is where you will have the problems. So if that is the case, then with high probability, the induced PDF will be different from the exact PDF, right, for the observable. So we use what we call this data consistent condition. The data consistent condition says that basically the error is dominant in the mean square error, approximation in extreme event regions when there is no data available for extreme events. That's what the data consistent condition says. Basically says that the error, as you can see on the left, which is the error on the non-extreme event regions, it's smaller or it can be bounded by the error on the extreme event region. That's the assumption, which again is reasonable. And under this condition, we have shown that essentially the Weissenstein distance, it's between the induced PDF through the approximate map and the exact PDF, it's greater or equal than the error that the map does in the extreme event region, right? And again, the interpretation is that when the data is limited, a data consistent map is never good enough, especially when it comes to metrics like the Weissenstein distance that takes into account extreme events. So a small distribution gap can be devastated for the tail. That's the idea. So you see that the error that you do for your map approximation at the extreme event region is the one that eventually creates the problems. All right, now a direct result of this is that if we further assume continuity and some additional technicalities, then we can show that if the Weissenstein distance tends to 0, then the map will actually converge in probability on the correct map, which basically guide us to define the problem as follows. We should not just drive down the mean square error in the standard sense, but also try to drive down the error with respect to the probability density functions of the observable. That's the key idea. So we define this new class of learning problems with the optimization as follows. We want to find a map, U, that minimizes the distance from the data in the standard sense that you see here, right? That's the standard mean square error minimization. But we also want to minimize the distance of the statistics, right? So this is the induced PDF through the learn map and the target PDF. So you have two terms, right? You can like, it may remind you physics-informed neural networks, but now you don't have physics. You have statistics-informed neural networks. That gives an interesting acronym, SINS, which we avoided. So this is, but you can think of it as SINS, right? It's statistics-informed neural networks, but statistics in the sense of extreme events. That's the big thing. And why did we choose W1? Why did we choose Weissenstein and not something else? I mean, there are some theoretical arguments, and that gives you optimality and practical benefits. Like if you want to use something else to represent distance between statistics, it's okay. I mean, that's one like nice thing, that optimality of W1, basically, or choice of W1, it basically tells you that W1 is tight for extremes, right? It bounds from above and below the distance of, or the error of the map at the extreme event region. This is all nice properties. There are some practical considerations. I'm happy to talk about it, like how we implement that numerically. There is some sort of technicalities. Again, I'm happy to discuss about it. Nothing like very heavy, but it needs some sort of thinking. Let's see some examples just so you get an idea, right? So we start with a 2D to 1D toy problem. Essentially, let's say that the red on the left is the map that you are trying to approximate, and the observable in this case is the output of this two-dimensional map, right? And as you can see, I'm sampling on purpose everywhere except on this large bump here. So I'm basically missing in my original data set and my initial data set, not my initial, in my data set, I miss completely this region where you have actually an extreme value. If I do mean square error optimization, no surprise, this is what I'm going to get. Basically, very good description in the regions where I have where I have data points. If I now apply eta learning and I basically encode this information that, hey, there is some non-trivial statistics that cannot be explained by this model, and you have to come up with hypothesis maps that they explain, the statistics I observe. Then you will start getting things like that, right? Where you have the correct picture where you will have data, and then you have an extra bump. And why do you have that? So that I can explain the statistics associated with the true map. So with the map I observe, I put there, I start getting, of course, produce statistics by the approximate map that are consistent with the blue curve, which is the truth. The green line is the statistics obtained from the mean square error map. So obviously, they are not correct because there's no reason to be correct. And the key thing you have to keep in mind is that there's not only one scenario that can explain a certain observable, the statistics of a certain observable. So here you see just different realizations. For example, this one seems to be very close to the real thing, to the true one. And there are all sorts of possible scenarios, right? Now, one can ask, is that good? Well, that's the best you can get, given that, again, you have zero data for extreme events. The only thing you have here is an observable that is telling you there is something, but, might be many different explanations that can explain the statistics for a given observable. How is that solvable? Well, more observables, I guess. Okay, so we go to a 2D to 2D example, right? Where the observable in this case is what you see on the top right. And these are the two maps, right? Two-dimensional output. And this is how we start with. And this is what we get in terms of realizations. Much better in this case, right? Of course, the mean square error, has no idea that there is something there, simply because, it relies only on the data. And good statistics, and agreement with the statistics. And these are different versions, again, that you can get by running this in a generative way, because every time you run it, you will get something different, meaning a new explanation of where the extreme events may actually happen. So we now apply this to extreme precipitation events. We essentially consider a data set, ERA 5, and this is the US, continental US, and we basically consider the spatial maximum every 24 hours on each grid, and the observable in this case is the maximum precipitation on its daily peak snapshot, right? So over space for a given day, we find where the maximum is, and the observable is basically, the statistics of this spatial maximum. Okay, so we are trying to create a downsampling algorithm that will be able to explain extreme events. That's the idea. So we are given a very, very short amount of training data, supervised training data. The supervised problem is basically going from low resolution to very high resolution that you see at the bottom. And again, if you go from low resolution to high resolution, there is big ambiguity on how intense the peak of this extreme event is going to be. This is where the problem is. This is what we're trying to fix, right? So if you do downsampling, the pattern will look nice, but you will not be sure whether it's like, how bad this peak is. That's what we're trying to solve. And the way we solve it is to complement this very short, data set of 0.5 years of supervised learning data, with the accurate statistics for the spatial maximum of precipitation. This is based on 25 years of unlabeled data, right? So this accurate statistics for the spatial maximum is simply based on 25 years of unlabeled data. So we apply eta learning, and we want to compare basically the generated snapshots through the eta learning process with the statistics obtained from 25 years of high resolution data, which we also have available as a benchmark. All right, so the results, sample snapshots. So low resolution input is at the top line. These are three realizations, three events. That's the high resolution truth on the second row. And the mean square output, this is what you would get if you will just do a downsampling based on mean square training that people typically do. And this is what you get if you do this eta learning idea. Essentially, you see that the difference between mean square is exactly at the peaks, right? So the peaks are more pronounced, and this is associated with the fact that it tries to explain the statistics obtained from the unlabeled data. So PDF comparison, that's very important here. Essentially, blue is ground truth based on 25 years of data. Red is what we have constructed, the eta map, right? That mimics very well the statistics. The green is the mean square downsampling, right? Does not do great. And yellow, it's essentially the training data, the labeled training data we're using for learning the eta map, right? So that's, you see basically that there are no extreme events. That's why we have the yellow curve in the training data. Now, the other interesting question that we tried to solve, we said, all right, if we can do this, let's try to do it for even hypothetical statistics. In other words, let's say we have, climate, we're not allowed to say climate change, but let's say we have some sort of very disruptive crisis, and we want to fit a generalized extreme value distribution, right? We are not going to use the unlabeled statistics, unlabeled data statistics, but we'll just want to see how these catastrophic precipitation events will look like in a world where the statistics are very heavy, the tails are very heavy. So this is the idea. We are essentially training again using the very limited data of 0.5 years, but now we're trying to explain a PDF that looks like the purple one, right? Much heavier than the blue one. Blue is the truth, the unlabeled data, but now we want to see how the downsampling will look like if we have something way more severe. And this is the idea. You see that, again, we have the low resolution input, 3 events, high resolution truth, right? That's what we have for validation, mean square. And now we have an output that is way more pronounced, like way more intense, again, because we are trying to explain a PDF that has much heavier tail, even with the truth, right? So you see that the generated events are way more aggressive compared with the high resolution truth. So ETA learning in that sense, it can be used to even understand like climate change scenarios and this sort of very hypothetical things that some people are still interested in. I want to close with some papers. This new work, the Extreme Event Aware Learning, it has been submitted. It's in the second round of review. Hopefully it will be published soon. And I want to thank you for your attention. I'll be happy to take any questions. Thank you very much.
Thank you for the talk. We're giving applause here, but we won't deafen everyone by listening to them. Any questions? All right, I can get us started then. In the ADA learning framework that you talked about, there was this uniqueness issue, we'll call it, where depending on the different run, you might have different possible results. Could you use the generation of a series of different possible results as some sort of metric for determining subsequent samples that you would take? Like
that's a great question. That's what I have in my proposal, actually.
Okay.
Yeah, that's the idea. The idea is that you generate a large number. You can generate 50, 100. It's easy. If you do it, it's super easy actually to generate as many. You can do clustering. Like it's not that this space of possibilities, it's huge. There are probably 5 or 6 clusters in most cases of possibilities. And then, yes, you can use that to do active sampling because now you have an idea of what the extreme events will look like. That's the next paper we're writing.
Cool, thank you.
I think I also have a question about
Sure.
the ADA learning framework. So you said that if you had multiple observables, you can do better with nailing down the actual distribution. Can you just take random projections of the observable that you do have and like build new observables off of that? Or is it because it's dependent on that first observable that you won't be able to?
You can do in principle. I will tell you 2 problems we are exploring here. So number 1 is what is the optimal observable, right?
Mm.
So this is a very, how can I say, open-ended question. Like the second question is what is the dimensionality of the observable, right? My point is it okay to have 3 one-dimensional observables, or it would make more sense to have 1 two-dimensional observable? And then when you go to 2-dimensional observables, you have to deal with 2D distributions, which makes the problem more expensive, right? Because now you have to consider distance between 2-dimensional PDFs or 3-dimensional PDFs, and you have to take into account tails. So it is that's like again, like these are 2 very good questions, the previous one and this one. These are the things we're currently working on, meaning larger number of observables or higher dimensional observables. And understand the interplay of number of observables versus dimensionality of observables. But I don't have I think it depends heavily on the specific application we're talking about. But this is something we're also exploring at the moment.
Great, thank you.
Sure.
Other questions, either over Zoom or in the room?
The first 2 questions were exactly the things that we're currently working on. So I hope I hear the third question so we get inspiration about what we should do next.
All right, well, unless any last minute people come in, we'll thank you one more time for the talk. We're at the hour here, so natural time to end. Thank you again.
Thank you. It was a pleasure. Thank you, guys. Good to see you all.